Actually, let's see what we did last time. But in the meantime, good morning. How is everybody doing? Where did we leave off? Functional groups. Isomers, okay. Okay, well, we can kind of go from there. Hopefully you guys, good morning. Hopefully you have all seen the functional group stuff that I posted in Discord. Should be in there somewhere, probably in the extra kind of help part. And we'll talk about those in a little bit. So let's start for a bit talking about isomers again. So isomers, as we're going to see, come in a lot of different kind of types, I suppose would be the way to say it. Right now, we have constitutional isomers, which means that they're going to have the same formula but different arrangement of the atoms. And so that could be something like this 5-membered ring with the oxygen inside it, now becoming a 4-membered ring with a methyl group sticking out. These would be, I don't know why I put an arrow there, these would be constitutional isomers of each other. If we were to try and take a look at their chemical formulas, we'd say, okay, 1, 2, 3, 4, 1, 2, 3, 4 carbons in each. We're going to have 2 hydrogens on each of those carbons because they all have 2 bonds, so they need 2 more hydrogens. On the other one, we're going to need hydrogen, 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 hydrogen. We're going to have 8 of those. Or again, I'll just draw them in because we're still learning these. That's H8 and then O, right? So we have many things that we can do with this. We could also even go crazy and say, okay, well, instead, let's say we have now for something like that. That would also work. This has the same formula. So with a double bond instead. So all of these are constitutional isomers of each other. And so unfortunately, it's a tough question for me to say, well, hey, take this formula and give me as many isomers as you can. There are so many. And so that's why, again, kind of molecular formula for us, that could cut it in Gen Chem because, sodium chloride, who cares? There's only one thing. But when you have organic molecules, you're going to see you can get, dozens of structures out of just one formula. And we're going to see that those will all behave very differently from each other. So it's different. And so we could even have, let's say now, I put it over here instead. Like, that's a different isomer. So lots of different things here. So that's kind of what we mean there. Okay, so we're going to see later on, we're going to have geometric isomers. Which we've kind of talked about in 113. We had cis-trans isometry. Those are geometric isomers, just depending where things are in relation to each other. Even though like the connections are the same, sometimes things are pointing up or pointing down. Those things will matter. We're going to have stereoisomers. That's something we're going to cover in Chapter 5. This is going to be something that we've not really talked about yet, that you will learn to love. We'll see. Uh, that'll be later on. And that's going to be everything is the same, but one thing might be different in another molecule. Something like geometric isomer, I'll just give you a couple of examples. So these ones, oh my gosh, these ads are so annoying. Ignore that as always. These two are geometric isomers. So they have the same connections. So we saw that, with constitutional isomers, they have different arrangement of atoms. Yeah, right. These have the same connections. So, like, the carbon, those two middle carbons both have a chlorine on them, so the connections are still the same. But geometrically, they're locked in one position versus another. We're going to see later on that double bonds cannot be rotated around, but single bonds you can rotate. But with double bonds, you're stuck in place there. And so having both of those on the same side, both chlorines on the same side of the molecule, is a different geometry than having them on opposite sides. And those are called geometric isomers. We'll talk about those later when we talk about alkenes. Stereoisomers are ones where, like, this will be a much more complicated type of isomerism rather, not isometry, where we're going to see that kind of just one thing is swapped and they'll actually form mirror images of each other. But that's something later on we're going to talk about in chapter 5, but those are also isomers. So we'll talk about those later. So same connections and all that. These only have single bonds, these stereoisomers, so there's free rotation around. Double bonds you can't rotate around, so geometric ones are locked in place. But stereoisomers, you're going to try and rotate them as much as you can, but nothing's going to happen. So we'll see those later on. But I just wanted to kind of throw them out there, that there's other types of isomerism that we're going to talk about in this course. So just keep that in mind. So right now, just constitutional isomers. That's just the same formulas, same number of atoms, but they're arranged in different ways. Okay? Cool. Let's talk about carbon, nitrogen, and oxygen, and formal charge. When we go through these. One thing to remember, formal charge, technically, is your number of valence electrons minus your number of bonds minus your number of lone pair electrons. I'll write that out. And that's not number of lone pairs, that's how many electrons are in lone pairs. But we're going to have kind of a cheat sheet. It's going to make things a little bit easy for us. But let's talk about carbon first, because carbon is our favorite element in this class. So we know carbon has 4 valence electrons typically has 4 bonds. Let's take a look at, say, formaldehyde. Carbon here has 4 bonds. It has 0 lone pair electrons. It has 0 formal charge. Generally, again, we see this happening. But let's say we got rid of one of those H's. And now we have carbon like this. And I'm going to, in fact, explicitly put in my lone pairs here. So this carbon normally has 4 valence electrons. It has 3 bonds. It has no lone pair electrons. And so it has a positive 1 charge on it. And so you'll just want to remember how to calculate formal charge. If we instead had same thing, but now had a lone pair there. There, I'll be nice. I'll even write in the C for us right now. We have 4 valence electrons, 3 bonds, 2 lone pair electrons. Remember, a lone pair is 2 electrons. And so we have a negative charge on this carbon. And so that carbon has a negative formal charge. All right, neither of those are likely to happen. There are other circumstances where we'll have what are called carbocation or carbanions. Remember, cation positive, anion negative. So those are specifically ones of carbon. So, kind of cheat sheet here. For carbon, let's see, how do I want to do this? Let's do the formal charge here. So this is for carbon. If we have a number of bonds, number of lone pair electrons. If you have 4 bonds and 0 electrons, you're in good shape. That is neutral. If you have 3 bonds and no lone pair, you have a positive charge on your carbon. If you have 3 bonds and 2 lone pair electrons, you're going to have a negative 1 charge. So, examples. If you have methane, we'll say. We're going to see that, why did I draw a bond to it? This one's going to be negative, this one's going to be positive here. So normally 4 bonds, that's its ideal. If you have 1 fewer bond and no lone pair, it's positive. If you have 1 fewer bond and a lone pair, then it's negative. And so that's kind of what the types of carbon we're going to see. Again, this one is called a carbocation. And this one is a carbanion. We're going to see carbocations will become a pain in your behind. Carbanions less so, because carbocations really ruin molecules. But that's something we'll talk about later on. So for right now, I'll just understand that they exist. They're called carbocations, and I've done something very specific here. These, in fact, are sp2 hybridized, and therefore are trigonal planar. Because they don't have that lone pair, they're going to be, those hydrogens are going to be pushing as far away from each other as possible. And remember, since now we only have 3 things on our carbon, it's going to be trigonal planar, and it's going to be sp2 hybridized. But the carbanion, we still have 4 things, right? If we harken back to many years ago now, actually just last year, we see that the right and the left are both tetrahedral, because there's 4 electron domains. However, the one in the middle is going to only have 3 domains, and so it's going to be trigonal planar. So just keep in mind, carbocations are always going to be trigonal planar, and they're going to be sp2 hybridized. The other ones are going to be sp3. because they're tetrahedral. 4 things. So 3 things only, so sp2. Alrighty. Let's talk about nitrogen. Yes, that at least is consistent. So we're going to have its formal charge, we're going to have its number of bonds, and number of lone pair electrons. So, with nitrogen, we can look at the same. Oops. Yeah. We're going to see these are kind of the flavors of nitrogen that we're going to see. Typically, we're going to see that this one is going to be our normal nitrogen. So if we think of our favorite nitrogen containing molecule, that is ammonia. 3 bonds, 1 lone pair, or 3 bonds and 2 lone pair electrons is our standard nitrogen. We saw if we give it an additional hydrogen, remember this is ammonium, hopefully we remember that that's a positive one. So we see that if our nitrogen has 4 bonds, that's going to be our positive 1 case. And if we wanted to do the math, we'll say, okay, yeah, we have 5 valence electrons, 4 bonds, 0 lone pairs is positive 1. So that guy is positive there. And if we take away one of those hydrogens and now have a second lone pair, we're going to see we have 5 valence electrons, 2 bonds, 4 lone pair electrons. And so that's negative 1 overall. And so we're going to see that that's going to be nitrogen. So ideally, our nitrogen will make 3 bonds and it'll have its lone pair. And that'll be kind of normal nitrogen. Nitrogen prefers 3 bonds, and then it's okay, it's good to go. One thing to note, all of these, by the way, are all sp3. That's consistent at least. All of those have 4 electron domains, so they're all going to be sp3 hybridized. So nitrogen is always going to be sp3. But it can be positive or negative. It just depends how many bonds you're looking at. So normally 3 bonds is happy nitrogen. 4 bonds you get positive. 2 bonds you're going to get negative. So that's going to be nitrogen set. All right, any questions on nitrogen? We've already seen the first 2 many times, right? We've seen ammonia and ammonium. So those, we have amide is the last one there. But we'll see that more later on. Okay, so its formal charges will depend on the number of bonds, just like with carbon. All right, we're never going to be removing lone pairs from nitrogen. It's too electronegative for that. With carbon, we do sometimes see carbocations. We don't see, with incomplete octets like this, carbon here only has 6 electrons. We don't see that with nitrogen or oxygen. So only carbon can have this incomplete octet. And as we see, that's going to be unstable, and that's why you're going to hate them later on once we talk about carbocation migration. That's right, carbocations will move throughout your molecule and ruin it. But we'll get that nightmare another day. Let's talk about oxygen. Its formal charge, number of bonds. So oxygen likes to make 2 bonds, right? It has 6 valence electrons. It's going to make 2 bonds to fulfill its octet. So that's going to be our normal oxygen. For a no charge oxygen, it's going to have 2 bonds and 4 lone pair electrons. Here is our water molecule. Our standard neutral oxygen has got 2 bonds and 4 lone pair electrons. If we take one away, replace it with a lone pair, that's going to be negative. You're seeing a pattern here. We take away a bond and we replace it with a lone pair. That makes things negative. If we give it an extra bond, though, that's going to make it positive. So if you really want to do the calculations, we have 6 minus 1 minus 6, negative 1. Here we have 6 minus 3 minus 2, which is plus 1. And so if we want to see our oxygen with 3 bonds will be plus 1. Our oxygen with 1 bond will be minus 1. So just keep those in mind. All right, so it's just going to be easier for you to be able to tell the formal charge just kind of looking at the number of bonds. So carbon likes 4, take 1 away. Depends if you give it a lone pair or not, but you could make it positive or negative. With nitrogen, if it has an extra bond, it's positive. If it's got a missing bond, it's negative. With oxygen, same thing. Oxygen likes 2. If it's got 3, it's positive. If it's got 1, it's negative. So those will be kind of patterns that we're going to see here. So that's why it's a good idea to always keep track of your lone pairs as you're drawing your molecules, so that you'll be able to tell the formal charge if you really want to calculate it. All right. Questions on those ones? Alrighty, let's talk about then resonance. So resonance, we kind of defined it in 111 as electrons that are kind of able to move around within a molecule to kind of either provide an equivalent Lewis structure or a similar Lewis structure. Right, so those are what we call delocalized. That means they're not stuck in one spot. Electrons that contribute to multiple Lewis structures. And we'll take a look at that. For example, if we have acetic acid, and I'm going to draw out the bonds here, we could see that an equivalent structure would be to draw it like this, right? I could draw the double bond to the oxygen on the other side. It doesn't really matter which one I do it to. And this is what resonance is. So those electrons, some electrons in this structure are able to move around. And so we're going to see that as a result, they're going to be equivalent structures or very similar structures. Sometimes we're going to see with resonance, we have better forms than others. We're going to see we could even go as far to say, we could resonate this and say, okay, here, I'm going to slow down and show how I got from the left structure to the right structure. How I did that, actually, this is not even a very good example to do this for. Okay, we're going to show you how to do okay. We're going to calm down for just a second here, and we're going to choose a different molecule. We're going to do benzene first. Benzene, as we know, one of our absolute favorite molecules, as you're going to see through this course. These electrons here are able to hop around, so we can move electrons within this molecule to end up getting In this case, it's an identical structure than the one we had before. It's a really bad benzene. Let me draw that one again. Here. So I've moved my double bonds. So if I were to arbitrarily number these, we see in the left structure we had 1 double bonded to 6, 2 to 3, 5 to 4. And in the other structure, I now have the double bonds between 1 and 2, 3 and 4, 5 and 6. So we have moved our bonds around, but we have ended up with, in this case, an identical structure. So if we were to just have rotated the molecule, we would still end up with the same thing. So, but this is what resonance is. So those electrons are able to move around. If we wanted to go really crazy with this, we could. Knowing all those carbons are sp2 hybridized, they all have p orbitals. And those p orbitals... I should have... Let me draw this a little bit sideways. Okay, there we go. Those p orbitals, how resonance is working is, so we have essentially 1 electron in each of these p orbitals. And that electron has a decision to make. Let's actually have a special electron in purple. Oh. We've lost our orbital. That purple electron could decide to make its pi bond with the electron below it or the electron above it. It could form a bond here, or it could form a bond there. Either way, right? There's not any, particular way it would rather bond. It's like, oh, you're an electron. Oh, you're an electron. I'm going to be with you. Okay, now I'm going to go be with you. And so those electrons are delocalized because they have the freedom to bond with each other. And so because we have all these alternating double bonds in this molecule, that means we have p orbitals that are all right next to each other, that all have that electron within them. They can decide to where they want to bond. All right, and so with one of them, let's say the green one, we end up getting this molecule. And if we do the purple one, we end up getting that molecule. And so either way will work. And so if the purple one decides to go with the top electron there, going to the structure on the right, well, then that other electron on the bottom is going to go bond with the electron to its right. So that's how it's going to work. So they're going to end up forming their double bonds in either way. And we're going to see that because they're all equally likely to kind of choose whichever one, that these structures are rapidly changing into each other. So half the time, the benzene looks like it is on the left. Half the time, it looks like it is on the right. Even though they're identical molecules, we'll just say maybe we've labeled these carbons, and so we'll just have it that way. So that's how resonance works. So we're able to move our electrons around because there are other orbitals to hold them. We can see also resonance can take place if we have something like this. Our carbonate anion. Oops. This will be the better example than doing acetic acid. But we could say, oh, you know what? I would rather bond with that carbon. Why don't you electrons go and hang out with oxygen instead? And so we'll end up with this structure instead. So we're moving electrons from a lone pair to form a double bond, and we're breaking the other double bond to form a lone pair. And in this case, again, the structures are identical, right? They're the same molecule, or ion in this case. And so, notice with these, we're often going to get the same molecule. Sometimes we'll have better ones. For example, it's a bad idea, but we could say that these electrons in that pi bond just decide, hey, screw you, carbon, I'm leaving. And if they do that, poor carbon here now is going to be positively charged. And all of these oxygens are going to be negatively charged. Notice still, though, in either case, we're still left with CO3 2-, right? 3 minuses and a plus is still 2- overall. This is another form of resonance, though this one is going to be less likely. We're less likely to have this. Unlikely to have this. And we're going to learn some rules for kind of how to do resonance, and then how to identify if certain forms of resonance are less likely or more likely. All right? So we're going to learn about it here. So, here is our first rule here. Rule number 1. Never break a sigma bond through resonance. So we can mess with pi bonds, we can mess with lone pairs, we're never going to mess with a sigma bond doing resonance. So that's the first rule. So never ever break a sigma bond, a single bond, during resonance. All right. Step 2, you can only ever start from one of two things. You can start from a pi bond or a lone pair. So you can start resonating, as in moving electrons around, from one of two sources. You can start from a pi bond, or you can start from a lone pair. Those are the two places that you can end up. Okay, and you can end by making a pi bond or a lone pair. So these are our kind of rules here. Never mess with a sigma bond. You start from a pi bond or a lone pair, and you end by making a pi bond or a lone pair. All right, so we're going to go ahead and see how this is going to work. We're going to see that in chemistry, organic chemistry, we're very often going to be drawing curved arrows to indicate the movement of electrons. And we're going to start by doing resonance. Later on, we're going to talk about how different molecules, their electrons are going to interact with each other. And so this is what an arrow looks like. It's very exciting. I'll try to be consistent by using light blue for my arrow pushing, moving electrons around. But this is how we're going to do this. So this part of the arrow is the origin. So that's going to be your lone pair or pi bond that you're starting from. And then this is going to be your destination. And so that is going to be something that makes a new pi bond or makes a lone pair. So that's how arrows are going to look. This is for 2 electrons. We're going to see later on, we're also going to use arrows for single electrons. And I'll do that in purple right now. If we have just a single electron, we see that it only has one thingy on its arrowhead. So we have 2 bits for normal arrows with 2 electrons. This is a 1 electron arrow. And they're the same thing. So this is going to be an origin and a destination. But this kind of what's called a fish hook is for 1 electron only. But for resonance, we're going to be always doing 2 electrons. So, but since we're talking about arrows, you'll also see fish hook arrows like this. Those mean 1 electron only. So normal arrows, you'll have 2. So if we are to take a look at our carbonate anion again, notice that if I'm going to arrow push, say I want to now make the double bond on the left one, notice how I am starting my arrow very clearly on that lone pair. So you want to be as clear as possible that I'm starting from that lone pair and I'm ending up pushing the electrons onto that to make a double bond. So I'm going to form a double bond here. All right, obviously that's going to put my carbon at 5 bonds. So, because that's not allowed, we can never have carbon with 5 bonds, we're now going to go ahead and break another double bond and move its electrons to make a lone pair on oxygen. And so as a result, and by the way, notice also I'm using this double-headed, what's called a resonance arrow, to show that all I'm doing is moving electrons around within my structure. So I'm not fundamentally changing the structure, I'm just resonating. So I'm just moving electrons around, it can go back and forth. As this happens, we now have our double bond there. We now have an extra lone pair on that oxygen. And now, I mean, our formal charges have slightly changed. They're in different places now. So that's how resonance works. So we're always going to start at a lone pair or a double bond, and we are going to end by making a double bond or a lone pair. All right. Typically, resonance will keep on going as well. You could stop it in the middle. Let's take a look at another example. And here, I'll even put an oxygen now. And we'll say that this oxygen is negatively charged. If I were to decide to resonate this particular molecule, I have 4 places to start from. I could start from this double bond, from that double bond, from that double bond, or from one of these lone pairs. So I have 4 places I could start resonating from. Four places to start resonance. All right, so I'm going to decide I want to start at number 4. I want to start off with one of those lone pairs. I shouldn't have used here. Let me redo these ones in a different color so I can be consistent with my arrows being light blue. So So I have 4 places I can start resonance. Those are all places we can start. I'm going to choose to start on 4. I don't have to. I could start somewhere else, but I want to start at 4. So I have options. I can push those electrons down to make a new double bond. If I do that, I have options. Well, I could now take the electrons from this bond and form a lone pair on that carbon. Or I can keep pushing things around, and now that one ends up on that carbon. Let's take a look at what those look like. So if I'm just doing the blue arrows only, if I do that, this is what my molecule is going to look like. We're going to end up with a lone pair on that carbon. That's something we definitely need to draw in, because otherwise we might think it's a carbocation or that it's got 2 hydrogens on it. Resonance, you never are breaking any single bonds. You're also not making new single bonds either. So that carbon originally had 1 H on it. It still has 1 H on it. So it's important that we notate that there's that lone pair there. Carbon with a lone pair, as we may remember, is negatively charged. So we've essentially, through the resonance of the blue arrows, just moved our negative charge from the oxygen now onto a carbon. If we take the purple route, here, I'll start from that lone pair. If we do the purple ones, we are going to now have our lone pair on that carbon at the end, thereby making that carbon negative. We have our 2 lone pairs left on the oxygen, and so we'll have just shifted our double bonds around, and so we'll end up with something like that. Do we see how I was able to get these 2 structures by resonating? And do we all see as well how I'm being very careful about where my arrows are starting and where they are ending? So I'm trying to be as careful as I can, showing exactly if it's starting from a double bond, I'm showing exactly where that double bond is that I'm starting from. Or if it's a lone pair, I'm showing exactly where it's starting from. And I'm very careful to either end it on an atom, giving it a lone pair, or on a bond, making a new double bond. What colors am I still? Okay, I've got this one. Notice this arrow here. I'm going to erase this circle in a second, but notice that I'm very clearly starting from a double bond and I'm ending up on an atom. That's that blue arrow there. All right, limiting that one. Notice with this arrow, I am starting on a double bond, and I'm going to be forming a new double bond. So I'm pushing it onto a bond that's going to make a new double bond. All right, so you can push onto an atom to make a lone pair, or you can push onto a bond to make a double bond. So those are your 2 options. That's all we can do with resonance. But as you can see, I'm going to have a whole bunch of resonance arrows here, or resonance forms here. And the third one I could make Well, I could do this instead. I could instead end up with my lone pair on that carbon, if I were so inclined. I could do that, right? How might the arrows look to make this one happen? This is going to get, oops, I should not forget my lone pairs there. With resonance, you always want to put all your lone pairs on all your atoms, so that everything is as accident-free as possible, we'll say. All right, oh my gosh, I'm out of colors. Okay, whatever, we'll just do it with dark blue, we'll say. So if I want to end up with my lone pair on that carbon instead, and I'm still starting from my oxygen, I could totally do that. Well, I could say I'm going to do this arrow and then this arrow, but instead of that next purple arrow, I'm going to end up putting my electrons there instead. So we have options. We have a lot of different options on what we can do here. So let me actually just draw them in the dark blue. So, okay. I could do that. So those two purple arrows are the same, but instead of continuing on, I'm going to throw it onto that carbon instead. All right, so with these dark blue, blue, I can end up resonating onto that other carbon if I were so inclined. And so these are just resonance forms starting on that oxygen. And so we're able to see that I can distribute that negative charge wherever I want. I mean, not to say wherever I want, but I have 3 other places I could end up putting that negative charge. And so that's delocalizing it. It's allowing it to be spread around through resonance. So remember, all these resonance forms are, contributing to reality. So that lone pair is able to move around throughout this molecule. And so that's the idea of resonance. And so we're going to see later, resonance is a very important factor in stabilizing molecules, because things don't want charges, right? Organic molecules do not like to have formal charges. And so we're going to see that resonance is one way to accommodate those by sharing the burden of that negative charge, in this case, among many different atoms. And so that's going to help stabilize this particular molecule. All right, does anybody have any questions? Oh, okay. Yeah. So, yeah, you'll never be able to isolate one of these. Never, ever. All of these are components of what happens in reality. So if you were able to freeze time, you might be able to find one of these. But in reality, the electrons are just zipping back and forth. Electrons move at the speed of light, right? Or very close to it. And so these electrons are constantly moving around. So in reality, you just have that one extra lone pair there that's causing the negative charge. At certain instances, it's located at one of these atoms. But in reality, it's just spread throughout the whole thing on average. So just like with benzene, sure, half the time it's this, half the time it's this. And so there's totally multiple outcomes here as well. Most people will just say, forget it, I'm going to just put a circle in there to indicate, or more likely, so a circle is common, but in reality, people will just draw kind of a dashed line like this to indicate that those double bonds can move. And so that's the idea here. So if we really wanted, we'd say, these aren't real double bonds, they're partial double bonds. It gets a little bit hairy in terms of terminology. But these are all resonance forms of the same molecule. So That's what we call them because we understand that all of these all contribute to the overall structure of it. And so there's not one in particular in this case that is better than the others. Actually, the first one is the best, but we'll talk about how to identify that in a little bit. But all of these could exist. All right. What's not likely to happen, though, is something like what did we have? This was our original molecule. What's less likely to happen is that these electrons just randomly decide, aha, I will go here now. I mean, it's allowable through our resonance rules. If we do that, but now we end up with this. The electrons have left that double bond. They've decided to leave. This is a resonance form of this molecule, but it's less likely that this bottom part is ever going to happen. It's allowable, but unlikely. So we would say this is a very minor contributor. So we call all of these little bits resonance contributors or resonance forms to the overall structure. This one on the bottom here is not likely to happen. The reason for that is now we've added extra formal charges to our molecule. Now we have two negatives and a positive. And so that's less likely to happen. All right, so let's talk about rules. So, good resonance, i.e. major contributors, will do a few things. The first one is to minimize formal charges. So if we see this top structure, we have a negative charge. We see the bottom structure, we have two negative charges and a positive charge. The top one is better. We want to minimize the amount of formal charges that we have. Overall, it's still -1, but why are we going to make that poor carbon have an incomplete octet, and we're going to make that other carbon now have an extra electron, and so that's going to have a negative charge? Not a good thing. So we're going to see that better Lewis or better resonance structures, more likely to happen, more likely to be major contributors, are going to minimize formal charge. So we want to have as few charges as possible. Sometimes that's not possible. All of the ones of this molecule have a negative charge. No way around that. But what to do if you have to have a charge? If a negative charge is present, we have kind of options here. To the most negative, electronegative atom, so a better resonance form, if you have a negative charge, is to have it on the most electronegative atom in your structure. Remember, those are the ones farther to the right. So carbon is the least electronegative, then nitrogen, then oxygen. So if you have a negative charge and you can give it to an electronegative atom, that's better. That will give you a better resonance structure, a more likely resonance structure. If that's not possible, if there are no heteroatoms in your structure, the best thing to do with a negative charge is to give it to a terminal carbon. That means a carbon at the end of the molecule. And we're going to talk about why that is a little bit later. But for right now, I'm just going to give you all the rules at once, and then we'll talk about them. So terminal meeting at the end of the chain. So again, carbon usually forms chains, right? So ideally, you'll give it to the most terminal carbon if you have to. All right, with those two rules in mind, two and a half rules, I guess. So looking at some of the structures we've drawn before, in fact, our best structure, according to all of these rules, is the top one. We have a negative charge. There's no way to get rid of it. The negative charge is already on the oxygen. That's our most electronegative atom. So that's going to be our best resonance form of the rules that we know. That's going to, in fact, be the most likely. You're most likely to find this molecule looking just like this as drawn. All right, but let's say we're trying to rank the other ones. And so, if we're trying to rank the other molecules, the next best one is going to be this one, because we've put that negative charge at the end of the chain. So that is better than the other two, because those other ones have internal negative charges, so they're interior of the chain. If we're to say which of those is better, I'm not going to expect you to do that. These would probably be about equal to each other. So of these forms, those two would be approximately equal. But we're going to see that the first form up here with the negative on the oxygen is the best. And then the next best form has the negative on the end of the chain. And then lastly, we kind of have these with the internalized negative charges. And then I guess if we're really crazy, this would be like way down there. This would be very unlikely because now we have extra formal charges. So that one's just making things a whole lot worse for itself for no reason. So that's extremely unlikely. All right, so I don't even want you to include, for example, these unlikely contributors that have extra formal charges. Like that, there's just no point in doing that. Even though you can resonate that way, just don't. It doesn't help things. All right. Does that make sense, though? So we're able to kind of rank these from best to worst, I suppose. Cool. Alrighty. If a positive charge is present, ideally, if possible, give it to the least electronegative atom. That's typically not something we're able to do, though, because positive charges mean deficiencies of electrons, so it's less likely that you're going to be able to move it to the least electronegative atom. Electronegative atom. But if somehow you're able to, might as well. That would mean a carbon. And we're going to see that we're going to have the opposite rule for the negative charge. So if we have a positive carbon, we want it to have to be the most interior, or what's better to say is the most substituted carbon. So I'll explain that. Give it to the most substituted carbon. As in the carbon that has the most non-hydrogen things. And let's look at a couple of examples like that. So okay. So here's a structure. Okay. So we have three carbocations here. we're going to see that carbocations are most stable when they are internalized, when they're on the most substituted carbon. We have words for these that we'll describe. This one is called primary, which is written 1 degree primary. This one is secondary, and this one is tertiary. Tertiary carbocations are more stable than the others. We'll talk about why in just a little bit, but for now, bear with me and accept it. A primary carbon has one other carbon it's bound to. So let me just define these, I suppose. Primary or terminal carbons are only bonded to one. So yeah, all these various substitutes can be called. Yeah, you can have primary alcohols, secondary alcohols, tertiary alcohols for sure. Absolutely. But just identifying what primary, secondary, tertiary means. Secondary carbons have 2 carbon-carbon bonds. And tertiary carbons, you even have quaternary ones, but that's those are boring. You can't have a carbocation that's quaternary anyway because carbons can only have 4 things. So do we see how the carbocation in this leftmost example is primary? That carbon that it's on, the leftmost carbon there, has only one CC bond. That carbon at the very end only is connected to one other carbon, therefore it's primary. The middle, this carbon right here, is connected to a carbon on the left and a carbon on the right. So it's got 2 carbon-carbon bonds. We call that secondary. And then the last one, this carbon right here, has got 3 carbons attached to it. And so that is a tertiary carbon. Or in this case, a tertiary carbocation. All right, so these are things we're going to see a lot. So definitely take these vocab words to heart because we're going to use them a lot. So with resonance, a tertiary carbocation is the best place to stick a positive charge if you have to put it somewhere. All right. The opposite case for negative charges. Negative charges want to be on primary carbons. All right, they don't want to be on carbon in the first place, but the best place to put one is on a primary carbon. All right, so I will I'll include that here. Oops. So those are the best place to put those types of charges. All right, if you have to put them on carbon. Well, I guess the cation is more likely to go on carbon anyway, but that's that. So let's take a look at a couple of... no, there's one more rule we have. If both a positive and negative are in the same molecule, and they can't be gotten rid of, if you can't do anything with them, put them close to each other. As close to each other as possible. All right, so sometimes a positive and negative you can put together and make a double bond, you're great. But sometimes you can't, because maybe that'll give it too many electrons or something. And one example of that is, let's say we have this right here. We have a negative here. All right, we could resonate this if we were so inclined. A couple of ways to do that. If we want to resonate this, let's say we're going to resonate it from that double carbon-carbon double bond. We could do it. Let's start. This is going to make it terrible, but we could. Let's make it terrible. If we do this, let's take a look at what happened to that carbon. So that carbon there, if we were to redraw it, whatever, who cares about the rest? We still have an H here. If I got rid of that double bond and I moved it, so if that double bond's gone, and now it's over here, note we're now left with a positive charge on this guy. So while I didn't really draw it, we're not adding any HCH bonds or anything, so that carbon had 2 CH bonds and a C double bond C. We broke that double bond. We moved the electrons away from it. We now have a carbocation there. So don't forget to always kind of keep track of that. But notice what we've done here now. So is this any better? I'm sorry, that oxygen, this oxygen is not negatively charged. Now it is, though, now that we've given it that extra one. Is this structure going to be better or worse than the last structure? I think this one's going to be worse. Right? Even though, yeah, now we have, you know, another negative by a positive or something, we're throwing in 2 more formal charges that really have no purpose being here. So this one's going to be worse than it was before. We have made our molecule worse than it is. We made it less stable than it was originally. Poor molecule. But let's say we have a different molecule, because I can do that. I have so many molecules. If we resonate this one, we might make it better this time by doing something very similar. If we go ahead and start at that lone pair, start pushing things through. Notice that, again, I could, if I really wanted, push that lone pair. I could do this purple arrow instead. Generally it's just not a good idea to do that, because now I'm putting a negative charge onto a carbon. Generally not the best thing to do, especially when I'm putting it in kind of on a secondary carbon there. So let's ignore the purple arrow. Oops. And so what happens with this structure is now I get, let's see, I get this as, I'm sorry, we should have those things there. And so we ask ourselves, is this one any better than the last one? I'd say it probably is a little bit better. Because now we have these negative charges. In both cases, the negative charge is on an oxygen. So we still have it on an electronegative atom, so that's a good thing. Again, we can't get rid of it, unfortunately. We can't just say bye-bye, random negative charge. Can't do that. So we're not adding any more formal charges in. We're just moving them. I still have them both on oxygens. That's good. And so the last criterion is... Oh my. Bo is, we'll just say playing with one of his toys. Yes, I would say it's better because they're closer to the positive charge. Yeah, so the nitrogen there is positive. The right one is probably slightly better because now we have the negative charge, instead of it being way out in the middle of nowhere, is now slightly closer to a positive charge. And so that's just going to be a little bit easier for that nitrogen, because now that oxygen has extra electrons. It can help stabilize the positive charge of the nitrogen. Since we can't combine them, right? We can't just say, oh, I'm going to just actually get rid of that negative charge and have this now. Right? This is a big no-no. What have I done? I have done something very naughty indeed. And put 5 bonds on this nitrogen. That's a no-no. So we cannot get rid of the negative charge. So best thing to do with it, if it can still be on an electronegative atom, put it next to a positive charge. So as close as possible. And so this will be slightly preferred. It's probably not a huge deal, but better. It's preferred to have that negative charge next to a positive charge, if we have to have it and it's still on an electronegative atom. So, all right. We are going to spend so much time on resonance because it's such an important concept in this course. You do have a number of homework questions on resonance, but we're definitely going to be doing more. All right, but are there any questions on that one? All right. Let's take a break from resonance there. We're going to start more resonance on Wednesday. Are you guys Monday, Wednesday? Yeah, Wednesday. We'll do a little bit more, not a little bit, we'll do plenty more resonance on Wednesday, but I want to talk about a few things that are going to kind of help us handle resonance. So, some kind of patterns here. We're going to see that some substituents, remember, a substituent is a non-hydrogen on a carbon. So anything that's not hydrogen is a substituent. We're going to see that substituents can either be electron donating, meaning they push electron density in towards something, or electron withdrawing. And so we're going to see that sometimes things take electron density away. And we're going to see there's going to be a number of different substituents that will either be pushing more electrons into our system, and that means we're more likely to kind of start resonance, so they're the origin. Those are going to be things with lone pairs, lots of lone pairs, lots of electron density to push electrons away from itself. And these are going to be more likely to terminate resonance. And I don't mean like to make it happen, but I mean that's where you're going to end your resonance. So you're going to end them at electron withdrawing groups. I don't know if you guys can hear him like panting. You are exerting yourself, mister, by being naughty. Yes, we see you down there. But what I mean by these common electron donating groups are amines or alcohols, those are probably your most likely places to start resonance, because notice these have nice lone pairs for us to start our resonance there. After that, we're going to have ethers. Ethers can donate electron density as well. He's just having so much fun. And what else do we have? We can have esters a little bit too. Those can donate electron densities. And then finally, just what are called alkyl groups. Those are just carbons. Carbons donate electron density into a system. So these do not have lone pairs to like fully donate an electron in, but we're going to see this is the reason that carbocations, when they're tertiary, are more stable than primary or secondary ones. All right, ones that are likely to withdraw electrons are nitro groups. That's that NO2 there that we saw. Notice that we ended our resonance at the nitro group. It's a good place because it's withdrawing electron density. Notice we started at an oxygen that could have been an alcohol, but we've deprotonated it. It's a good place to start resonance from, and we ended at the nitro group. So we're going to see that that's a good place as well. A sulfonyl group, SO3, is a good place to dump electrons, a place to throw your extra electrons away. We can also have carbonyls. So let's see. Because if you resonate towards a carbonyl, you can now push electrons up onto that oxygen. So you can resonate towards a carbonyl. That's good. Likes to happen. Those are electron withdrawing. And then we also have, we can have esters as well, but on the other side. So here, let me be a little bit more consistent. So whatever this black thing is your molecule. So whatever your molecule is, whatever you're looking at, that's where it's connected on all of these. So if it's connected to the nitro or connected to a carbonyl, that's good. Those are good places for it to be. We could also have esters, but the other side, those are places you can dump electron density. And then we can also finally have halogens. Where X is a halogen. Those are also good things that can withdraw electron density. So sometimes, the last rule was to put positive and negative together. With these halides or these alkyl groups, they're not going to have full charges for us to mess with, but they might have partial ones. So, for example, perhaps we remember this, but if we just have a molecule like this, I mean, there's not going to be any resonance for this one, but just showing you how this works. We have a dipole here, right? We have a partial negative fluorine, and therefore a partial positive carbon here. That's the dipole, right? So this is called induction, by the way. That slightly positive carbon is potentially a good place to dump electron density if there was a space. There's no space in this particular molecule to put any more electrons in, but let's say if you had to put a negative charge here, that might not be the worst thing in the world. It's still secondary, it's not great, it's probably still better to put it on the primary carbon, but because it's at least next to a partially positive thing, that's slightly better, right? So it's not the worst thing in the world to have that. So we're going to see when we talk about acid strength, later on this inductive effect will become pretty strong. So this can kind of withdraw electron density, and therefore allowing more electrons to be put in. So if you have to push electrons towards this, that's a good thing, because that fluorine is taking away electrons just through its polar bond right there. And so if you're going to be giving more electrons nearby, that's not the worst thing in the world. All right. And just to start this part, why is this carbocation better? The reason for that is because carbons, I'm going to draw them out here, through a process called hyperconjugation, can actually share electron density just a little bit. As these CH3s are rotating, I'm going to try and draw them in kind of a 3D here. So as this bond is... go away. So this bond is just rotating around, right? Single bonds, they just twirl around. As a carbocation just has an empty p orbital. But as this CH3 is rotating, that carbon with its hydrogens that are sticking out are rotating around, every so often, that H and its s orbital can kind of just a little bit share electrons as it's rotating around. And so the more of this that you have, the more random little s orbitals you have that can interact for just a brief moment with the empty p orbital of a carbocation, the more of those you have, the more hyperconjugation you have, the better, the more stabilizing it is. So, you've got the H's here as well. Oh my god, he is just going nuts. I really hope you can't hear him just panting, because it's like kind of disgusting. So this thing is also rotating around. All of these single bonds are just rotating. And so as they do, that p orbital that's just sticking up and down, okay, good. Those p orbitals can just get a little bit of overlap of electron density, and that helps to stabilize it. So as all these bonds are rotating, and then so same thing with this, what color I'm going to use? Dark blue. This bond is also rotating around, and you have those hydrogens that are going to just briefly overlap a little bit. So it is a very brief overlap of CH bonds onto an empty p orbital. And this is a stabilizing effect. So we're going to see that carbocations will prefer to be at these tertiary locations because that means they have 3 other carbons that have hydrogens that can help stabilize them. A carbon that is on the end only has 1 carbon that can help stabilize it. So because you have fewer things stabilizing it, it's going to be overall less stable. So this hyperconjugation idea, which is just these brief momentary overlaps of orbitals, help things out. I'll try and find maybe a video or something, just a quick little video explaining hyperconjugation more, because it's kind of not so easy to picture because things are moving so quickly. If you have, though, your molecular models, it may be good to just build this particular molecule. And if you have specifically an sp2 carbon that you can put that on, you can rotate your methyl groups around. Those are those CH3s. Those are called methyl groups. And you can see as you're rotating them that for a very brief time they might be aligned with that vertical p orbital. And so if you have your models, you may want to just do something like this so you can see the hyperconjugative effect in not real time, but in something like that. All right. So a couple things for you guys to do. I would keep learning your functional groups. So alcohols, ethers, amines, esters, all those. We're going to still talk about them, but it's a good idea for you to still take a look at them. And what else do I want you to start? Still just kind of practice resonance. We're going to talk about that some more on Wednesday. We're going to do a couple of more examples of resonating things and identifying which resonance forms are better than others. So that's kind of what I want you to do for the next couple of days. You do have a homework assignment. It does have resonance. It does it have? Yeah, it has functional groups on it too. Yeah. I'll put some more on hyperconjugation, and we'll definitely do more with resonance on Wednesday. And if you guys still want some videos more on resonance, I'm sure I could find some. But for now, I'll just put one on hyperconjugation up for you guys. So, all right. It's fun stuff. I know we have a lot to do. Lots of resonance stuff. Lots of arrows and things moving all over the place. Best thing to do is practice it. So you want to get in the habit of drawing your arrows. Make sure they're very clear. And so the first homework, I haven't set a due date yet because we haven't covered everything. So if we talk about acid strength on Wednesday and we're done with it, then I'll assign a due date and it'll be 1 week from Wednesday. But if we don't cover it all, then it still won't be due. So don't worry about that. I will Canvas, I'm sure, will give you an alert because Canvas likes to throw out random emails. So it'll let you know. And then if I'll still write it on Discord, and I'll probably say it in class as well. That the homework will be due in a week from whenever I say that. So, okay, so for now, still no official due date, at least 9 days from now. So, but again, a good idea to start on it. So, alrighty. Yep, that's what we're doing. So the first couple of weeks, there's a lot of foundational stuff here. So we have a ton of material in this course. It's really actually quite unfair because the second semester for OChem is so much easier than the first one is. Is it a holiday? Oh, crap. Okay, well, I'm still gonna stream on Monday. Even though it's a holiday, I will give that up for you guys. You don't have to be here. I mean, you never have to be here, but I think we need the more practice. So next week I'm still gonna stream on Monday for you. Okay, so that'll be up there. So, uh, but I won't for my other class. So, but I mean, just for example, you're gonna see these. Oh, I should definitely save this. Um, I know we're just a little bit over time, but I had OChem 2 this morning. Um, with this sort of thing, you're going to see these arrows are all over the place. So these are reaction arrows, they're not resonance arrows, but they're super important. And you see, again, I'm very clear when things are starting from bonds versus starting from lone pairs and where they're going. So these arrows are going to be super important for you throughout OChem. And notice again here we have primary and secondary things happening here. And so I don't want to scare you, but getting this stuff down is super important. That's the lesson here. So I'm going to go ahead and post these notes up for you so that you have them. And wait a second, we still have Wednesday. It's not the weekend yet, if only. If only it was. What class is this? 221. Alrighty. That's it for today. I'll see you Wednesday. Do your practicing stuff. Throw your questions out. Not like throw them out of the trash, but throw them on Discord and we can go over them. So, see you guys on Wednesday. Take care.